Alright, so all of that theory and equation derivation is really kind of fun, and it definitely enhances the sexy mind. But on the other hand, it doesn't show you how it is that you might go about using this in a practical way. So I wanted to go through a question that might give us a bit of an example of how one might go about using and applying the Michaelis-Menten equation. And of course, it has to be true that if you're going to use this equation to describe an enzyme, well, then that enzyme must have to follow Michaelis-Menten kinetics. And in a more practical terms, what that means is that it's not going to be an allosterically regulated protein with multiple subunits. It's going to follow that sort of hyperbolic curve that we see for the Michaelis-Menten equation. So we have this enzyme then, we'll say, that follows Michaelis-Menten kinetics. It has a KM of 4.0 micromolar. And what we want to know is if the initial velocity of this enzyme is 0.23 micromoles per minute at a substrate concentration of 5 micromolar, what is the initial velocity when the substrate concentration is doubled? So we'd be looking at going from 5 up to 10 micromolar. That would describe a doubling in substrate concentration. Now let's remind ourselves that of course this is going to be describing then, or the equation here will be describing the curve for this enzyme. So we will be seeing then of course the traditional rectangular hyperbolic curve approaching of course the Vmax value as described on the axis there. So Vmax would be here. Of course we would have Vmax over 2 at a substrate concentration of the Km. So we know that, actually we're given that value. We know that the Km is 4.0 micromolar, so we already have that given. And we also know that the initial velocity at the substrate concentration of 5 micromolar is 0.23 micromolar per minute. And you know, just qualitatively, to think about this for a minute, we know that we recognize that 5 micromolar is above the Km. So we would recognize that at this substrate concentration, we certainly have gone past the region of the curve that is going to be described by that very rapid and linear increase in concentration. So we are out beyond the Km value with this substrate concentration. Now doubling to 10 is going to take you way out beyond that Km value. So let's go ahead with bearing in those things in mind and go ahead and use the Michaelis-Menten equation to help us figure this. So we'll just get that written down, remembering that that equation is V naught is equal to Vmax times substrate divided by Km plus the substrate concentration. And we're given the information that at 0.23 micromole per minute, that velocity occurs when the substrate concentration is equal to 5.0 micromolar. The Km again is 4.0 plus 5.0. So we just go ahead and work that out and solve for Vmax. Give us a second constant. We know that Vmax is a constant, as is Km. So if we get both of those, we should be able to do the rest of our calculations. So if we work all that out, solving for Vmax, we come up with a value of 0.414 micromole per minute. So that's the value of Vmax right there. That's going to be that constant. So I'm going to go ahead and circle that. Now we have the constant for Km. We also know Vmax, and we have a value. We can plug in those values for a value of substrate at 10 micromolar and see how that changes initial velocity, because that's what we want to know, is how is initial velocity changed by that doubling. So I'm just going to go ahead and erase some of this so that we can plug in to see how that doubling changes things. Alright, so initial velocity would then equal 0.414 micromole per minute times substrate concentration now is 10.0 micromolar divided by Km we know to be 4.0 plus 10.0 at this second substrate concentration. So initial velocity, after you pump all that through, you guys can go ahead and enter that into your calculator and see what you get. And the value that comes out there is 0.30 micromole per minute. Okay, can really only retain two significant digits there. So what that means then is, look at that, at a concentration of 5 micromolar, the initial velocity is 0.23 micromole per minute. After doubling substrate concentration, we see that the initial velocity is 0.3 micromole per minute. So this is only an increase of 0.7 micromole per minute. So that clearly shows us that we are on the point on the curve that has begun to level out. So when we change from, say, a substrate concentration of, say, 5 to 10, and those are not quite on, but what I'm showing you is that we're in a region, we can tell by this, where things have begun to level off. No longer are you down in that linear region of the graph. So this is a really cool way to see that graph come to life in terms of checking and seeing at different substrate concentrations what sort of a change does that cause in initial velocity. So I did a horrible thing here. I didn't really label my axes very well, right? Because of course that y-axis is initial velocity and this x-axis is substrate concentration. So the concentration of substrate there. Okay, great. So that's a nice example of how you might put all of this into action and actually see the Michaelis-Menten equation allowing you to calculate velocities as long as you know some of the other constants. We see then that Km and KCAT are both really important values in terms of understanding an enzyme, both its efficiency and how much it desires its substrate. But how do we go about finding those? How do we determine what the KCAT is or the Km is, and how do we do that based on such a convoluted hyperbolic graph as we see that normally describes this function? So I guess that is one answer, is by looking at that normal plot, and just to remind ourselves by again and again about this plot because it's so important, where we have initial velocity as a function of substrate concentration with our hyperbolic curve. Well, you could say, hey, you can determine Vmax because it is the value that the function approaches. That's true. It is. That's hard though. It's an asymptote, right? So we know it's approaching that forever, and so actually getting a value for that Vmax can be difficult at best. Now, certainly with the right computer and the right computer program, the equation describing this hyperbola can certainly be used to do that, to explain not only and solve not only for Vmax, but also, of course, for that substrate concentration Km that happens at 1/2 Vmax. But this is a tricky way of going about things, and so in order to simplify the determinations of Km and Vmax, and certainly once you know Vmax, right, you can solve for KMAT, because we remember the equation that allows us to do that, where Vmax is equal to KMAT times total enzyme concentration. Sorry, that is an E in there, and that's a T for enzyme total. So we know that those two can be calculated based upon one another as long as you have a real accurate determination of the absolute amount of enzyme that was added. So those two could be calculated from one another. So let's talk about some easier ways, though, of getting Vmax and Km, and then therefore making it easier to get KMAT. And the first method that's a bit easier is termed the double reciprocal plot, or also known as the Lineweaver-Burke plot. Well, let's go ahead and look at that. What happens with this is that basically the double reciprocal is taken, and by that we mean that the value on the y-axis is the reciprocal of initial velocity, and then the value on the x-axis is the reciprocal of substrate concentration. This allows then for the function that is described to be a much simpler function. In fact, it is a line. And the best thing about it is that the intercept, the y-intercept, is equal to 1 over Vmax. And the x-intercept is equal to negative 1 over Km. That sounds easier already, doesn't it? Because we know that this line is just simply going to have the standard equation of y equals mx plus b. And we can make that a little more specific for this particular line, right? Because y, we know, is 1 over initial velocity. M, rise over run, right? So 1 over Vmax divided by run, rise is 1 over Vmax, run is 1 over Km. That looks messy, doesn't it? And really all it is Km over Vmax. So let's rewrite that. Just a quick note that can be simplified. So Km over Vmax, okay, times x, which is 1 over the substrate concentration, plus b. Okay, so b we know to be the intercept, right? Awesome. So this is the equation of the line described by this function, and in fact it shows you right off the bat that we can calculate, if we know the equation of the line, we can calculate both Km and Vmax, excuse me. So what if I said that we had an equation for the line that basically was y is equal to 0.4 x plus 0.2. Okay? There's a couple ways that you could use this equation of the line to allow you to calculate both Km and Vmax, right? One way that you could do it is just simply by using what you know from this equation. So you could just say, oh, I see that 1 over Vmax equals 0.2. So you could just do that. 1 over Vmax equals 0.2. And then basically just taking the reciprocal of that, right? So Vmax then and that is going to be equal to then 1 over 0.2 which is then of course a value of 5. And on your graph, if this were giving you the equation for a line, of course the units would have to be specified there, like 1 over substrate in micromolar, and 1 over initial velocity in, micromole per minute or something along those lines. So it'd be, micromole per minute. Okay, great. So then that would give us Vmax in micromole per minute. Cool. So then we could go ahead and we could figure, now that we know Vmax, we could figure Km by just simply knowing right here that Km over Vmax is going to be equal to 0.4 on the equation. So let's erase and go ahead and do that. All right, so Km over Vmax equals 0.4, and we now know Vmax is 5, so Km equals 0.4 times 5. Okay, and then that just equals 2. Excellent. So then that should give us the value in micromole for substrate concentration. Now there are other ways that you could also go about doing that, right? You could also just say that I know that when the x value is equal to 0, so at the y-intercept where x equals 0, set x equal to 0, that would give you 1 over Vmax as the value there. So if you just go back to having your equation, right? So again, y equals 0.4 x plus 0.2. So we know that when x equals 0, y is 1 over Vmax. So let me actually just plug in for that. So this is going to be 0 plus 0.2. So again, 1 over Vmax, 0.2, which is exactly what we got the other way. Vmax is going to be equal to 1 divided by 0.2, or 5. Right? Same exact calculation, really, just different approach to it. You could do the exact same thing for finding the Km. Because you recognize that negative 1 over Km is equal to x when the y value is 0. So we would say at that 0, 0.4. So subtracting then, we'd have divided by 0.4 equals negative 1 over Km. Okay, excellent. So basically this is negative 1/2 is equal to negative 1 over Km, or Km is equal to 2. Excellent. Two different ways to go about the exact same thing, but you should get the same values regardless of how you plug in there and how you use the equation. So this line Weaver Burke plot is another way to go about things where you're graphing 1 over initial velocity versus 1 over substrate concentration. Much simpler way to get the values of Km and Vmax, and then thus from the value of Vmax you can sometimes go ahead and calculate the value of KCAT. So as long as enzyme concentration is known, right,